Good evening, folks. Welcome to the Northern Ireland Science Festival on this Wednesday evening online. Uh, this evening, we have down the line, all the way from New Zealand, Laurie Winkless. She is a physicist and a science writer. She's just recently released this book, which you may or may not be able to see in my really awful screen, which is Sticky, the Sacred Science of Surfaces. She's also a contributor for Forbes Magazine, and she has worked with schools and universities, the Royal Society, and the Naked Scientists. Laurie, it's great to have you with us, and we'll just take it away.
All right, thanks, Andrew. I'll share my screen.
No worries. Being your host, there we go.
Thank you. Now let's get into it. Hello, everyone. It's really nice to kind of see you all, I suppose. I'm really sorry I can't be in person. I would absolutely give anything to be in Northern Ireland at the moment. I would love to be there, but New Zealand it is. It's already Thursday morning here, and yeah, it's all good. So let's get started. I'm here really to talk to you all about friction, and specifically some of the forms of friction that will have seen many of us stuck to our seats in the past few weeks. We're really going to talk about ice and snow and winter sports. So this is inspired by my book that Andrew mentioned, Sticky, the Secret Science of Surfaces. It's a bit of a crazy whistle-stop tour through the world of friction and surface science. It covers topics like paints and adhesives and glues and kind of post-it notes and other famous products. We then talk about the gecko, arguably the most famous climber that we have ever known. We then move on to how we move through fluids. So hydrodynamics, how we move through the water is covered, and aerodynamics, how we move through the air. We're then on to motorsport. I'm a big Formula One fan, so there's a whole chapter dedicated to that. And now that I live in New Zealand, earthquakes have become just part of life here. We had a little rumble the other night, and that's fairly typical these days. So I've written all about how friction, the role of friction in earthquakes. The next chapter is the one we're mostly focused on today, and that's a chapter about ice and what it is that makes ice slippery. But I also talk about the human sense of touch. And then finally, in the book, we delve into the atomic realm to try to understand what happens with friction when we just have a few atoms in play. But today, we're just going to focus on one specific topic, and that is the friction of the Winter Olympics. So we're going to get into it, starting with ice. Now, producing the perfect Olympic ice requires three key things. The first two are a very well-designed rink, so some good infrastructure in place, and secondly, very pure water. Now, most competition level rinks have concrete bases that are also sitting on sand or gravel. And within the concrete, there is a network of pipes embedded. And before you can form ice on that concrete slab, you need to cool it down. You need to get it to temperatures below freezing. So to do that, you pump a saline, a salt-based solution known as brine through this network of pipes, and you wait. The temperature will gradually drop, and at some point will get to below freezing. So this is a pretty gradual process. It is a slow process. And then once the concrete has reached the kind of temperature range that you're aiming for, the cooling system is left on continuously. So if you have any sort of dedicated, a year-round ice rink, the cooling system will stay on all year round. You really don't want to have to remake the ice very often. It's quite energy intensive, so they tend to just keep it on. So now we've got a lovely cold concrete slab ready to go. So now you need water that is as pure as possible. So tap water, distilled water, they're just not good enough, although they are a pretty good starting point. Those types of water have lots of impurities in them, so things like salts and fluorines. They make no real difference to the quality of the water in terms of drinking. In fact, those impurities are actually what give water its flavour. But if you are a professional ice maker, those impurities are a nightmare, because what they do really is they alter the molecular structure of the water, and that will have an impact on the type of ice that you can make from that water. So typically a professional ice maker will start with good quality water, tap water, and they'll pass it through a series of specialist filters. Now, most international grade arenas, like you will have seen at the Olympics, they use a system called reverse osmosis. And this forces water through these kind of one-way membranes, and it strips a lot of contaminants away in the process. You then pass it through another series of filters. These are usually called resins, and their job is to remove any charged particles. They're harmless in water in terms of drinking, but again, we want to get rid of them so that we have as pure water as possible. That also gets rid of some of the minerals too. Now, ice makers are obsessive about monitoring this water as they're producing their ice. They are constantly monitoring things like the water's electrical conductivity, just to make sure that it meets the exacting standards that they have set for the water for competition. I mentioned that there are 3 key ingredients. The third one are, in fact, the ice makers themselves. Now, these are often called ice meisters because what they do is a real skill. You will have seen some of these ice meisters if you've watched any of the Olympic Games. Often they're the ones who are driving on to a rink during a break and play. These machines are usually called Zambonis, and that's actually a brand name, but kind of like the Hoover, it's become the name that we use to talk about ice resurfacing machines. And that's a really important maintenance step that they will do during a competition. But the ice meisters do more than that, because they are also the people who have taken the ice from, or excuse me, the rink from that kind of concrete slab into the ice surface that people can skate across. Now, while most Olympic host cities will have their own kind of internal team of ice makers, they will very often also hire in, bring in overseas experts who have done other Olympic Games. Now, one of these people you can see on the image on the left, and this is Mark Callan. And in this photo, he's producing a very specific type of ice that we will talk about in a little while. And Mark told me that before an Olympic Games, he will arrive in the city many, many weeks in advance, sometimes several months in advance. And then they spend almost the entirety of that time making the ice for the competition. This is a very slow, very methodical process. And that is because each rink and each track has its own specific type of ice. Not all ice is created equally. Every discipline at the Winter Olympics has its own set requirements. It's all water, it's all using the same ingredients, it's all below freezing, but its behavior varies a lot. So let's just look at a couple of those sports. Now, hopefully some of you will recognize this athlete. This is Erin Jackson. She had just won the 500 meters long track speed skating event at the Olympics. And just as an aside, as well as now being an Olympic champion, Erin is also a material scientist by training, which I think is mega cool. But in her race, Erin covered 500 meters in just over 37 seconds, which means she was traveling at about 49 kilometers per hour. Now, there's a lot goes into trying to travel at this speed and being able to travel this quickly on ice. Part of the reasons is that these athletes train very hard and are extremely fit. Their technique is important, their body position, their rhythm that they use as they skate, all of those things are really important. They've also got these fancy suits that you see. And the job of the suit really is to keep everything as smooth and sleek as possible. You're trying to make your body as aerodynamic as you can, reducing the aerodynamic drag. The skate blades as well that she's wearing are very specialist. They've got a hinge on them, which allows it to make good contact. But the blade itself is also very thin. At its thinnest point, it's about 1 millimeter thick. So it's very little of Erin in this case is actually touching the ice. but the ice itself still has a massive, massive role to play. Long track speed skating ice is the coldest, hardest ice of all Olympic sports. The surface is absolutely flat and level, and it only measures about 2.5 to 3 centimeters in thickness. But installing it takes about 14 days of continuous effort. So they do what you would expect. They cool the concrete layer down, they flood it with a very, very thin layer of water, then they put a very thin layer of paint, a specialist paint, to give the colors that you see onto the track, then some more layers of water, then some more paint to mark out the logos, etc., and so on and so forth. After about 20 ultra thin layers of ice, they're pretty much ready to go. They'll then use something like a Zamboni, a resurfacer, to just smooth the surface and trim it and make sure it's exactly flat. The other interesting thing about long track speed skating ice is its temperature. And just take a note of this temperature because we are going to talk about it in a little while too. And next in the kind of ice hierarchy is the ice used for ice hockey. This is a very different sort of sport than long track speed skating, so it needs a slightly different type of ice. Now you can see the thickness is actually fairly similar to a long track speed skating rink, but its temperature is a little higher. So ice hockey ice is a little bit warmer and therefore a little bit softer than the ice we've already discussed. The process kind of follows the same steps again. Layers of ice and paint, continuously frozen, etc., etc. This takes about 30 layers of ice because they use a slightly different technique. But that softness, that difference in temperature does make a difference. The difference it really makes is that these ice hockey players can change pace. They can have these kind of explosive changes of pace and direction that really characterizes the game. They also have slightly thicker blades than the long track speed skaters. They're about 3 millimeters thick at their thinnest point. So that combination is what gives them that little bit of extra friction they need in order to change direction suddenly. Now I've put two sports in here on the same slide because in many events they'll actually use the same venue. So short track speed skating, you've probably noticed now that this thickness is a little bit higher and the temperature is a little bit higher also. So again, it's still very cold, but it is still a little warmer than the previous types of ice. And short track speed skating, most of a race is spent going around bends, going around corners. So although they don't need very much friction, they do still need some in order to get the grip that they need to safely go around corners. Ice skating, so figure skating, it actually uses the thickest, warmest ice of the Olympics. Because if you think what a figure skater has to do, a lot of it is digging their blades into the ice in order to be able to leap from the surface, do their crazy impressive spins and flips, and then land safely. So they do need a softer ice in order to be able to do that. It takes about 3 hours to switch between these two types of ice. Usually they'll start with the short track speed skating ice, the event will happen. Then when everything's done, they will allow it to warm up slightly, they'll add some more layers and they get it ready for the figure skating event. But I've been mentioning this idea that ice gets softer, even at these temperatures that are well below freezing, excuse me. But why is that? I haven't actually told you why that is, and you shouldn't just believe me, right? Let's take a drink. So to understand what is going on the surface of ice, I just need to briefly interact you with a very important metric, and this is mu, the coefficient of friction. Now mu is a ratio. It's a number that tells you something about how two surfaces will interact with one another. And more specifically, mu is the ratio of the friction force that resists motion between surfaces and the normal force or the supportive force that a surface exerts on an object sitting on it or sliding on it. Now, this number is used a huge amount. It's used everywhere in physics and engineering. You can determine the value of mu between two stationary objects, in which case you're talking about static friction, or between two sliding objects, in which case you're talking about dynamic friction. Now, either way, no matter which type of mu you're defining, the closer its value is to 0, the more easily two surfaces can slide along one another. So just to give you an example, here are two coefficients of friction: steel on ice, like the blades, like the bobsleds that we see at the Olympics, much lower than that of rubber on dry asphalt, which makes sense. Rubber is there to keep us on the road. But what has mu got to do with ice's changing behavior? And while we're on that, why is ice slippery at all? Now, part of the answer to this is that ice, like many solids, develops an extremely thin layer of a liquid, a kind of semi-liquid, at temperatures well below freezing. And this layer can be somewhere in the range of 1 to 100 nanometers in thickness, extremely thin. And this layer is called pre-melting, and it was discovered a very long time ago. We've been studying it ever since, and quite recently, Japanese scientists finally managed to take an image of this semi-liquid layer on the surface of solids. But why does that form? Surely if something is below freezing temperature, everything should be frozen solid, right? So I just want to introduce you to some research from a few years ago that really unpacked this mystery. In these experiments, a group of scientists took a steel ball and they dragged it along ice surfaces at different temperatures. So materials wise, this is very similar to the way that a skate blade, a steel skate blade, will interact with an ice rink. And they found some really interesting stuff. Now, first of all, this confirms something that I've just mentioned as we've been going through these slides, which is that ice behaves very differently at different temperatures. So I'm just going to show you a plot from the graph, and I'm going to take you through this, so please don't panic. On this graph, you can see the left-hand axis is labeled friction coefficient. So this is the mu that we just mentioned, and it goes from 0 up to 0.8. Along the bottom axis, you can see we have increasing temperature. So from minus 100 degrees C up to 0 degrees C. And we know that at 0 degrees C, ice begins to transition into liquid water. So just for now, I want you to focus on the green line. And what that green line tells you is that at very low temperatures, at minus 100 degrees C, ice is not slippery at all. The friction between steel and an ice surface is actually very high at minus 100 degrees C. No one is able to skate on ice at those temperatures. And if you now follow the green line, you can see that as temperature begins to increase, that high friction gradually decreases. So it decreases pretty steadily with increasing temperatures. And it reaches a minimum value. Its lowest value is at minus 7 degrees C. Now we need to flip over to the blue line. And between minus 7 and 0 degrees C, you can see that that blue line is basically vertical. So friction goes from decreasing steadily to very suddenly increasing. This is a very sudden increase in friction. And in terms of physics, this is a bit weird. Like, what is going on here? Why does ice's frictional behavior change so much? And what is going on down there at that mysterious transition point, that minus 7 degrees C? Well, on Earth, ice tends to take this very regular crystalline structure, and it means that each water molecule within an ice lattice is surrounded by and chemically bonded to 4 of its neighbours. But molecules on the surface of ice often don't have as many neighbours around to bond to, so some of them will be bonded only to 3 neighbours. Now, the difference between 4 bonds and 3 is pretty minor, but it does mean that some surface molecules of water can wiggle around a little bit. They can't go anywhere really, but they can wiggle around a bit. And what these two scientists found, well, is a big group of scientists, but the two leads are actually brothers. One's a chemist and one's a physicist. And what they found was that mixed in amongst these triply bonded molecules of water on a surface, there are some that are only bonded to 2 neighbours. Now, the difference between 3 and 2 is significant in terms of mobility. These scientists found that the doubly bonded water molecules effectively roll around on the surface. They act as if they are tiny ball bearings. And it turns out that those doubly bonded molecules were the real key to understanding what is going on this friction graph. So at minus 100 degrees C, friction is very, very high because almost all of the surface molecules of ice are very tightly bounded to the rest of the ice. The whole ice bulk is hard and solid, and the surface is effectively very rough. It looks rough in terms of friction. So that friction is high. When the temperature rises, what's really happening is that you're giving energy to some of the molecules on the surface. And that allows some of those molecules to kind of shake off some of their bonds. And that's why friction gradually decreases. Those wiggly water molecules make the surface a bit more slippery. By the time ice reaches minus 7 degrees C, it turns out that the majority of molecules on the surface of the ice are now mobile. They are mostly those doubly bonded water molecules, which makes it very slippery. And as a big bonus, because those molecules can move around so readily, they can actually fill in any damage on the surface of the ice. So they could drag the steel ball across the ice, but the ice just could cope with it. It was effectively self-healing because of this high mobility. The rest of the ice was still very, very solid though. Everything interesting was happening only on the surface. So the result is this perfect, very hard, very low friction surface that is a pleasure to glide across. So in terms of skating, this temperature, this minus 7 degrees C, is the sweet spot. Above this temperature, when we go into the blue part of the graph, what's happening there is that the surface no longer is the most important thing for the ice because the whole bulk of the ice is gradually beginning to soften. So it's not really about the surface anymore. That defines, that softness, that change in hardness defines its behavior. And it means that sliding objects don't just glide beautifully across the surface, they start to dig in, and so friction is higher. So this change from a material that can recover from deformation into one that cannot is why we get this sudden increase in friction. So now that we know all that, let's just take a revisit onto the sports I mentioned earlier. So speed skating happens at minus 7 degrees C, at that absolute sweet spot. It has a very hard, very cold surface that has low friction. So that's why speed skating happens at those speeds. It's where you can go fastest. Then ice hockey has slightly warmer ice. That means it is slightly less hard, but still pretty low friction. That combination enables the kind of agile motion that we see in the game. And then finally, figure skating ice is warm and it means it's fairly soft. It allows the athletes to be able to dig the blades in and to balance the kind of grip and glide combination that is so central to figure skating. So all that is to say that we now have a pretty thorough scientific understanding of something that these athletes and ice makers have known about through experience. Now, I've yet to mention my absolute favourite Winter Olympic sport, which is curling. I've left it till now because its ice is totally different from all the other ice. Curling ice is, you can see from this image too, but you'll have seen if you've watched any of it during the games, it looks different from other ice. Speed skating ice is very smooth and glossy. Curling ice is quite matte and it looks textured. And that is because it actually is textured. Curling ice is covered in these kind of a very dense pattern of ice bumps that are called pebbles. And this is what makes it dull and matte, but it also plays a really important role in the game itself. A curling stone cannot curl, it cannot take that bizarre path that we see on mirror smooth ice. It needs those pebbles in order to do that. Now you've already had a hint as to how you make this pebbled ice, and that's this photo of Mark that I showed you earlier. Making pebbled ice is something that no automated system has managed to do yet. It is entirely down to the skill and experience of the ice meister. So someone like Mark, they will create this very smooth, flat surface as before, but then they will walk up and down the sheet of ice, swinging a pebble head, this nozzle, with a bag of water on his back, and that creates this very fine mist of water droplets that once it hits the ice, freezes instantly. And they'll do this over and over again until they get a pretty uniform covering of these pebbles. They'll do it with different nozzle sizes. They might change the temperature of the water slightly. And it's a real skill doing this. When the pebbles are ready to go, the ice meister then does one last thing, which is they nip the top off the pebbles. And they do this using a very long blade. They drag the blade the whole way along the ice and nip the top off the pebbles. So rather than being rounded, they're kind of flat on the top. And that's also important. So if you're not familiar with the sport, I'm very sorry for you, but I'm going to just talk you through some of the basics in the form of GIFs. So curling involves two teams trying to slide these heavy granite stones from one end of the ice sheet to the next. And when a player releases the curling stone, as they do so, they rotate it, and you can see that they rotate it just before they pass what's called the hog line. And that rotation is very important. It's really what allows the curling stone to take its curling path. Then the sweepers, and I know people think that these are hilarious, but they are a very important part of the game. Their job is to sweep the ice directly in front of the stone. And what that is doing is effectively melting a very, very small amount of ice on the surface, which lubricates the stone's motion and helps the stone to travel a bit further. And if a stone has over curled or under curled, you can do a little bit of sweeping to help straighten out that path. Now, the goal really is for one team to have the largest amount of their stones closest to the center of a target, which is called the button. Ideally, you'd also kind of push your opponent's rocks out of the way too. And if you combine all of those things together, a very nice rotation, very nice delivery, then some really clever sweeping, accurate throwing, you can end up with an absolute killer curling shot. But there is something mysterious about how a curling stone moves on ice. So let's do a very quick experiment just with an empty beer bottle. Now you can do this with a mug as well. It doesn't really matter as long as it has a concave base. The bottom of a curling stone is not flat, it is concave, which means only a small ring of rock actually touches the ice. So let's have our beer bottle. If we set a beer bottle or any bottle sliding along a smooth table or countertop, you'll see it will just travel in a straight line. But if you do it while also giving the bottle a slight twist as you release it, so you want to set the bottle rotating as it slides along the table, you should see that the path will veer away from a straight line. The bottle will curl. If you rotate the bottle to the left or anti-clockwise, it should end up curling to the right and vice versa. And what's happening here is basically that friction is acting unevenly on the base of the bottle. So from the moment a sliding bottle leaves your hand, friction is working to slow it down. And as the bottle decelerates, it will lean forward slightly, which pushes the leading edge of the bottle further into the table and increases the friction there. Now, if the bottle is spinning as we release it, the leading edge will always have a bit more friction than the back edge of the bottle. And so what that really means is that the motion of the back of the bottle, the faster moving edge, is what dominates the direction of the travel. So in other words, if you spin it to the right, it curls to the left. Right, that's not that surprising in terms of physics. But it is funny when you ask a curler to do this because they're always a bit shocked by what happens with the bottle. And that's because if we do the same with a curling stone flouts the rules of asymmetric friction. a curling stone will curl in the same direction in which it spins, which is different from a bottle. And believe it or not, despite the sport having been around for like 500 years, we still do not fully understand why this is the case. Now, there are two leading theories on this to describe the motion of a curling stone. One is from a group of scientists in Canada, and their theory is called pivot slide. And in that, they say that the stone slides and rotates. As it does so, the microscopic roughness on the bit of the stone that touches the ice causes it to briefly stick to each one of these tiny pebbles that cover the entire ice sheet. And when I say brief, I mean many, many million times quicker than it takes you to blink. And although that contact between the stone, the rough band of stone, and the rough ice is brief, it does so many thousands of times along the length of the ice sheet. So if you can imagine that the stone hits one of these pebbles, it kind of pivots around the pebble and it can in the same direction as the rotation, and it pulls at it until it loses contact, and it does this many thousands of times along the sheet. Now, it seems that this motion is actually appropriate. It does reflect reality. It does reflect what we see in curling, and it is probably enough to describe a lot of this curling stone's behavior. And I say this because their theory is pretty well developed. They've got some beautiful equations that explain and describe pretty accurately a lot of what we see in a game. And we do think that this is enough to explain the motion. There is a kind of a competitor theory. Now, I should say that this theory is a bit less well developed. And this theory is from a group of scientists in Sweden, and they call it scratch guiding, which kind of tells you everything you need to know. The idea of this is that they say the base of a curling stone is rough enough that it can actually cause microscopic scratches to occur on the surface of the ice. So in this image, you're looking at an ice pebble, a flattened ice pebble, and you can see that it looks scratched along the top. So as the curling stone slides and rotates on the ice, the front of the stone kind of lays down these scratches, and then the back of the stone follows it as if it's a sort of a track. Now, this is slightly less well developed in that it doesn't have quite such good equations. It doesn't have quite such a good model, but it has been picked up by other research groups who are increasingly interested in it. So this theory hasn't quite gone away as yet. But at the moment, we really can't say precisely why a curling stone moves the way that it does. But that's probably enough about ice. So what about snow? A large proportion of the Winter Games happen outdoors. Now, the first thing to say is that I'm sure that most of you know this, but the Beijing Games are the first ones to have relied entirely on manufactured snow. Like other Olympics, the previous two Olympics have used manufactured snow, but Beijing has used entirely manufactured snow for its games. And in many ways, this manufactured snow is kind of similar to natural, or what we call dendritic snow, in that it is made from frozen water falling from the sky. But manufactured snow usually involves a system like this: high pressure water, special air cannons and nozzles, and they blow tiny liquid water droplets into the air that then freezes as it hits the ground. They will often add in some sort of nucleator, so some sort of molecule that the water can cling to and grow into crystals, which is similar to what happens in nature, but they have to add this in themselves. But manufactured snow doesn't form into snowflakes, right? So this is an image of the two types of snow for you. Manufactured snow is much more like kind of tiny balls of ice than these jagged six-sided flakes that we see in dendritic snow. And that has an impact on how the snow feels underfoot. So generally, natural snow is much softer, which is often preferred by skiers and snowboarders, especially those who fall over. But the dense, icy conditions of artificial snow does have some benefits. It is better for gliding on, and it is really good for making tight turns on. Now, just like with ice, each outdoor snow sport has their own unique set of requirements. But rather than engineering the snow to suit the athlete, what they do is athletes and their teams change the underside of their skis and snowboards, the surface that actually touches the snow. Now, for a 2-minute downhill ski race, what you really want is the slipperiest surface you can possibly get. You want to keep friction very, very low. But if you're doing a slalom event, for example, you do want some friction, right? But you are having to go through these twists and turns, so you do need some grip. And then in cross country skiing and in the biathlon, you will see athletes having to both speed across flat surfaces and also climb up hills. Now, the secret weapon that all of these athletes rely on is wax, slippery, water repellent compounds that are applied to the base of their skis and snowboards. And at high level events like the Winter Olympics, margins between competitors are absolutely tiny. So if you can find a way to manage friction, if you can use these waxes to ensure that your skis have the right combination of slipperiness and grippiness for each part of the course, it can really make all the difference. Now, I found one study that showed that if you reduce mu, so the coefficient of friction, if you reduce the friction between the ski and snow from 0.037 to 0.030, you can actually cut 6% off an athlete's finishing time. And in many World Cup type events, that is much larger than the difference between people who come in first and 10th place. So getting friction right really can make the difference between winning and losing. So therefore, it's probably not that surprising that big teams spend a lot of money and time invested in understanding this process and in developing the right combinations of waxes and other compounds to give skis the right level of friction. A lot of these teams will hire groups of wax specialists, wax technicians, who will often travel to the venue a year in advance just to get a feeling for the type of weather conditions they might experience. These technicians also put the skis on themselves and they test them out. They can try and compare different combinations of waxes dependent on what the weather conditions are on the day. And of course, athletes have their own preferences too. So the wax technicians play a really, really important role in these bigger teams. And typically they do use a combination of wax compounds. So in cross-country skiing, you'll see a combination of a very sticky, very high friction wax mixture that's applied just in the area under the foot and just in front of the foot of the ski. And that is what allows those athletes to climb up hills. But the rest of the ski is given a coating of a very low friction glide wax. Now, these compounds are added to the skis in many layers, and they're usually kind of ironed in place. So they're melted into place onto the base of the skis. But this process is very much more of an art than a science. It's all done through feel and experience and preference rather than a kind of controlled experiment. But that is likely and is already starting to change. And that's because of this stuff. Now, this is a molecule called PFOA. A lot of people also call it C8 because it has 8 carbons in the spine of the molecule. Now, this is a very slippery surface. PFOA used to be used in the manufacture of Teflon, so it really is slippery. And compounds like this, called fluorocarbons, they have been the absolute go-to ingredient for ski waxes forever. They are very good at keeping friction low. But the bonds between the atoms in PFOA are immensely strong, which means that this molecule doesn't break down in the environment. In fact, they accumulate over time and they are toxic, which has led to them being called forever chemicals. They really do stick around. And over the years, this has led countries and governments to decide to ban these types of compounds in a whole range of applications. And just a couple of years ago, the International Ski Federation decided that they would just ban them entirely from the sport, regardless of where the event was being held. They're starting with PFOA, that's the first one to be banned, but eventually it will get rid of all of these ultra slippery fluorocarbon waxes. So what are skiers and teams going to do once they're banned? Well, the first thing really is that wax technicians and teams are looking for other less damaging compounds to use on the base of their skis. And so far, these compounds are significantly less slippery than the fluorocarbons, but that will undoubtedly improve as and when more chemistry is done on these compounds. There's also a lot of experimentation around texturing the base of the skis. So etching different patterns into the base in an effort to reduce friction. Now, this is already done at the highest level of the sports, but there is some suggestion and some evidence that if we can shrink the patterns even smaller, we could potentially make them more effective. And maybe we could do away with waxes entirely. Scientists are getting in on the act too. So the Norwegian University of Science and Technology published a paper like literally 2 weeks ago. And in it, they introduced this new research facility that they have built. It's a 9-meter long indoor track that is covered in snow that they've made in the lab. And by attaching full length, real skis onto a pulley system that runs along the top of this track and applying lots of different loads onto the skis to simulate a skier being present, a skier's weight, they can measure the friction between the ski and the snow without having to do it on the side of a mountain, and even without having to put a human onto the skis in order to test it. And they've managed to do these measurements at very high speeds. Friction experiments are usually done at pretty low speeds, but they've managed to do this at 8 meters per second, which is about 29 kilometers per hour. That's a pretty typical speed for a professional cross-country skier to reach in a race. So experiments and setups like these will take a lot of the guesswork out of manipulating friction on the bases of skis. It just makes the whole thing much more quantitative rather than qualitative. And that should be a big help, especially as the sport moves away from these really damaging fluorocarbon waxes. So if you take anything at all away from this talk, I hope that it's friction and surface science. Those interactions, they're not some weird niche topic that are only for physicists and engineers. They're also not a dead area of science, as I was told by someone when I was writing this book. Every single thing we have learned about surfaces has unveiled further mysteries. Now, our knowledge of friction and the forces that act on and between surfaces has been honed since time immemorial, and it has allowed us to do some amazing things, not least to be able to race safely down a snow-covered mountain or to reach record-breaking speeds on a slippery, icy surface. Friction really is everywhere at the Winter Olympics. So thanks for your attention. I am very happy to answer any questions you might have.
Thanks very much, Laurie. We have, I don't know if you can see the Q&A from your side,
Oh,
but
yeah.
can you? Yeah, Laurie.
Yeah. I can indeed.
That's great.
So is different ice used for bobsled than monobob, luge or skeleton? Good question. Usually monobob, luge, skeleton, they all happen on the same track, and bobsled, they just do it so that the bobsled are the events that happen last because the bobsled does the most damage to the track. So they will also have ice meisters who do this. It's usually done by spraying though, rather than flooding, which is what the rinks are mostly doing. So it's not, one thing they're trying to do is to keep it as smooth as possible, but they don't have the same level of precision needed as they have on an ice rink. In saying that, I have seen some ice meisters who work on bobsled tracks who've said that, you know, if they get a bump and then they put another layer on, it becomes a bigger bump and a bigger bump, and it can be quite dangerous for the athletes. So that the ice is important. It's just harder to control because it's outdoors and it's experiencing much heavier forces, much heavier objects moving across it. So that's the first one. Second run of the 2-woman tobogganing, the commentator mentioned that it was 9:30 p.m. Temperatures were a lot colder than earlier. Yeah, and the ice was getting sticky. I now understand why it's sticky, but why? Yeah, very good question. Very good question. I looked into this as well and I couldn't find the answer. I think that the reverse order is deliberately there to kind of act as some sort of a handicap system, but I genuinely couldn't find a straightforward answer, so I won't try and fill in the gap, I'm afraid, Judith. Do any of the Winter Olympic teams have members who are physicists, material scientists? Heaps and heaps and heaps. Like I mentioned, Erin Jackson, she is a material scientist by training, but and there are lots of other athletes as well who have science backgrounds, but a lot of those working kind of behind the scenes. So a lot of the ice meisters, a lot of the wax technicians, they themselves are often scientists or have a background in chemistry or physics. Yeah, so there's loads and loads and loads of scientists working in there. Are computation methods such as CFD used to evaluate friction in different events or conditions? Yes. Friction is really hard to make any predictions around. It's incredibly difficult to predict what the coefficient of friction, it's impossible, in fact, to predict what the coefficient of friction will be between two surfaces. But we can take some kind of basic measurements and we can do some modeling. So yeah, that is used a lot. CFD modeling is used a lot. But what's been interesting is seeing, in some ways, kind of how old school a lot of friction studies are. They really are just dragging stuff on surfaces and measuring the forces. So although the modeling is really awesome, some of the experiments are still pretty basic, to be honest. So thank you for that. How do the material properties of the fake snow of the Chinese Winter Olympics compared to real snow? So the main thing is the amount of air that's in it. Fake snow has a lot less air than dendritic snow. So it does tend to be much icier. So it's more to do with the top surface tends to be a bit harder and a bit icier than real snow. And we, there's loads of questions, and actually this leads on to the next answer. The carbon footprint for creating the winter sport ice arenas, it's big. It is big. There's a lot of, people talking about how unsustainable the winter games are becoming, because so few parts of the world actually have the natural weather conditions to be able to host it. Like if you've seen any of the slalom events, for example, you'll see that every other mountain around the area is brown, and you just have this white strip of snow that's being created. So they 100% of the snow, other than some of the snow they had during the events themselves, a couple of days of small snow events, every single bit of snow at the Winter Olympic Games in Beijing was blown out of a cannon. So there is a huge question around that, and also around the ice arenas themselves. Depends on where you are. Usually the thing about carbon footprint is what's your grid? What does your electricity grid look like? And so, for example, here in New Zealand, our electricity grid is very green. Like we use a lot of renewable energy. So the carbon footprint of technologies that can be quite damaging in a coal-powered grid tends to be much lower in a more renewable powered grid. So it does really depend on that. But once you get the temperature down of the ice in an ice rink, it's not that expensive to keep it there. But yeah, the carbon footprint very much depends on where the power is coming from to do that. Other question. How do sleds in bobsled differ from how they interact with the ice? The commentators of bobsleds say how the Germans have better sleds. What makes them faster? A lot of it is to do with not what's touching the ice, believe it or not. A lot of it's to do with the aerodynamics of the whole sled, and the kind of micro motions that the athletes themselves make and how stable they can stay. That's actually a huge thing. But from what I can find anyway, the blades themselves on a bobsled are pretty standard. You know, they're not actually, there's not a huge amount of, at least that I could find, of innovation around the blade design. But I suspect it's mostly to do with it as a whole package, right? When we're talking about some winter events, it's only the surface interactions that matter. But in other events, the aerodynamics also matter. So it'll be some combination, just kind of like a Formula One car, you know, some will be better than others. Is the structure related to how the snow is made, i.e. so quickly, unlike dendritic snow? Yes, yeah. So you can produce it really, you can produce manufactured snow very quickly. And that does mean that it is kind of very, it's also very uniform, right? You're not getting the variety of snowflake sizes that you would get from snow falling from the sky. It's much more uniform. But yeah, the air is the key thing, really. The lack of air in manufactured snow is really the thing that defines how different it is from real snow.
Any
Cool.
more questions, folks? Nope.
Sweet.
It's looking good. Well, thanks very much, Laurie. That was, oh, yeah, no, we're all good. That was all
just a nice compliment. Thank you.
Just a nice compliment. Thank you, Owen. Thank you, Owen. Oh, wait, hang on. Jess says she has one more. Do you have one more, Jess? Are we good to go? Speak now or forever hold your peace.
You can always find me on Twitter as well. If anyone has any follow-up questions, I'm always on there, and my email address is on my website. So hit me up if you have any other questions. I'm always happy to answer stuff.
Okay, well, thank you so much. Oh, no, hang on. We've just had one more. Okay.
Two more.
Yeah, I'll tell you what. We'll do 2 more and then that's it.
Okay, all right.
We'll
So, Nicholas, do ice hockey skates generate more speed or do figure skates? Depends on who's wearing them, I suppose. Usually, I would say it depends on the ice too, right? As we've discussed. But ice hockey skates are usually good. They're the best for changing direction suddenly, more so than speed. But speed is really to do with the ice and the strength of the legs that are wearing the skates. Science of the clothing, friction in their outfits. Yeah, there's heaps of this I didn't even touch in it. In terms of aerodynamic drag, in terms of the materials that are used in their suits. You may have seen some news recently that shows just how cold it can get and how not at all insulating skiers' suits are. So there's definitely loads to be done in that. But really it's about smoothness. So in terms of their friction in their outfits, it's really about making the body as aerodynamic as possible. So you want something really tight, really smooth, that allows the air to slip over them as smoothly as possible. And if and when they wear helmets, they also want to make sure the helmets make them extra aerodynamic. So it's mostly just about hiding as much skin as possible, smoothing everything out.
Perfect. I think that's a great way to end this one. Thank you so much, everybody who tuned in, of course, to Laurie, who is all the way on the other side of the world to join us this evening. It's great for her to get her up. But you're totally talking to us from the future right now. You're talking
I am.
From
it's
tomorrow.
True.
Yeah. That's good. Thank you so much. And thank you so much, everyone who came. And if you are in Belfast, the book is on sale in our official bookshop, No Alibis bookstore on Botanic Avenue in Belfast. And I believe Laurie did send through some book plates, so you'll be able to get a signed copy as well.
I did.
Brilliant.
Cool. Thanks, everyone.
Thanks, folks.
Bye.